All right, good. Okay, so let's go back to the question. Oh, I should write down the time. So it started recording at 12:34. And this is practice exam number 4. Okay. So practice exam number 4, back to the question. And I'll kind of redraw it here. It looks like there's a little messy and it doesn't look like it kind of all copied. But this toroid kind of looks like the cross section of a donut here, kind of arcing around. Whoops, kind of missed that one. Here's kind of the center part of the donut hole. They said this first distance is 5, and the outer radius is another 5. So maybe I'll just do the whole thing as 10. Or did they mean this part was 10? The outer radius is 10. Yeah. So it's 5 to the inner radius and 5 more beyond that to the next radius, so a total of 10. And they put a current in here. And at least from our viewpoint, it looks like the current is in a counterclockwise direction. But I think the first step is to realize that the magnetic field is not a constant, but it changes with how far you're from the center of the donut hole part. So let me write down an equation we derived using Ampere's law for the magnetic field in a toroid, because what's crucial here is to recognize that the magnetic field changes with position. And so if I was making a blue here, and maybe I'll point out that they have a little loop of current here in the toroid at 900. And that would mean if I took my right hand and kind of curled it here, I would be pointing in to the toroid at that point. And so maybe I'll put a green circle with an X. And maybe I should even put the circles closer together near the inner radius and further apart at the outer radius, because this is saying that you don't have the same strength in the field. And that's an important step to realize here, because if you look at the forces on each of these wires and this equation, which says that the field gets weaker, this first part right here, let me call it wire number 1, and we'll just go around wire number 2, wire number 3, and wire number 4. But using the formula I equals L cross V and doing a cross product, I would put my fingers in the direction of the currents, rotate my wrist so I can close towards the field, and the force on wire number 1 would be, I'll call this inward towards the center of the toroid. Now, I suppose the good thing about wire number 1 is wire number 1 is laid out so that every part of wire number 1 is the same distance away from the center, and the equation for the magnetic field depends upon how far away it is. So really, wire number 1 is in a field that always has the same value. So this is going to make it real easy to calculate the force on wire number 1. We don't have to do the integration. That is, we don't have to say, oh, the total force is adding up a bunch of little forces, and adding them up would be the distance of that wire across the magnetic field at that wire. So had we been in a place where the magnetic field was changing, or for that matter, the angle, or for that matter, the current, but if any of those were changing, we would have to actually do this integral. And if none of those change, then we've got the simple case. And so wire number 1 is that way. But sadly, wire number 2 is not. If I look at the direction doing a cross product. The direction of the current would be this way. So I'm gonna put my wrist, my fingers in the direction of the current for number 2, and then I'll close towards B. And so the force on this top wire is down. And every piece is that way. But sadly, this is actually a lot harder to calculate the force on this because, as we see here, the distance would change for each little segment and the field would get stronger. So this part, I'll call it the left-hand edge of wire number 2, actually has a bigger force on it than the left-hand edge or the right-hand edge of wire number 2. So the forces are different, and so I'd have to add them up to get the total downward force. And so, bummer. That sounds kind of hard. However, I get a little more excited when I look here about wires 3 and 4. See, wire 3, current is going down, so I'll put my fingers down and close, my palm down, close, and I get a force going outward. And wire number 4, maybe can't really get over there, so maybe I'll turn the paper here. But wire number 4 with the current going up and then rotating my wrist so my fingers can go down where the field is. My thumb is pointing this direction. So those blue arrowheads are the direction of the forces on each of those wires. And looking closer at number 2 and number 4, they should have the same thing in terms of the magnitude, right? Because this first edge of number 4 is identical to the last edge of number 2, where the force is strong. And the last bit of wire number 4 and the first bit of wire number 2 would be pulling equal and opposite. So every little piece would be exactly equal and opposite. So the good news is I don't have to do that integral for wire number 2 and number 4. And I think that's why the hint is there. It says, hey, look at the top and the bottom segment. They look like they're going to be hard, and they wouldn't be too hard because an integral of 1 over r is just a natural log of r. So I don't know if I'd call it hard, but it's better if I don't have to do it. And so I don't have to actually calculate that. So when I'm trying to get the total force on it, I can see that I can ignore 2 and 4. And maybe I shouldn't say ignore, but I can justify that the net force from 2 and 4 is 0. And 1 and 3, they are opposite, but they're not equal. And so that's another thing to point out, that the field from the toroid changes with distance and gets weaker the further out. So the force that we could use, or this equation that we could use for the force on number 1, would have a different field than for number 3. So these two are equal and opposite, but they are not identical. So there is going to be a net force. And by that logic, since wire number 3 is closer to the center part, wire number 3 is going to have a stronger force on it. So the net force on this thing looks like it's going to be in the picture out towards the right. The force on number 3 is a little bit bigger than the force on number 1. Okay, but nonetheless, I will then calculate the values of them because I've got I'll just do the magnitude of force number 1. And we don't have to do the integral. This would just be I, L, B, and then the sine of the angle between them. So the I is the current that is going in this rectangular loop. So that would be 2 amps. L would be the length of the wire, which would be 3 centimeters. The B would be the magnetic field. So mu naught, I believe I read 900 turns to my toroid. Yeah, so 900. The current in the toroid is the 10 amps divided by 2 pi. Now we're going to have to look at the distance away. They said everything was centered up. So the magnetic field needs an R value measured from the center here. And so if the inner radius is 5 centimeters, then to the center of this rectangle would be another 2.5 centimeters. And then to this wire here would be plus another 1 centimeter. So that must be 8.5 centimeters to get to the position of where wire number 1 is. All right, so let's see. I did the current, I did the length of the wire. Now I just did the magnetic field. And now it'd be the sine of 90 degrees because the current is going up and the blue X's are going in. That's 90 degrees. So grabbing my calculator here, here is the force on wire number 1. 2 times 0.03 times, and if you'll let me save a little bit of keystrokes on my calculator by recognizing mu naught is a 4 pi, and there's a 2 pi already downstairs. I can cancel it off, and then I only have to type in a 2 times 10 to the negative 7 here, times 900 times 10. Sine of 90 is 1, so I won't do anything. Then divide by, it already took care of the 2 pi, so let's go 0.085. And so this is going to be 0.00127 newtons for the magnitude of the force on wire number 1. And everything would be almost identical for wire number 3. Because we'd still have the 2 amps, we'd still going down, so it's still 3 centimeters. We'd still have the free space. We'd still have the 900 turns in the toroid. We'd still have 10 amps in the toroid. But what does change then is that number, because wire number 3 is a little bit closer. And instead of being plus 1 centimeter further out, it would be minus 1. So 7.5 minus 1 is 6.5. And I only did it that way because I can save a little time, especially during a test, by just saying, all right, let me re-enter all those numbers. And then down here, the last one, instead of having 0.085, I have a 0.065. And I guess I should double check. That's still a 10. That's still 900. That's 2 times 10. And just everything else is still the same. And I'll just hit enter. So this is a 0.00166 newtons. And so to get the net force, as we already said, I have to add up all 4 wires, but 2 and 4 we argued come out to be 0, all right? And this 3 would be in the, what we might call the positive direction, and number 1 would be in the negative direction. And so if I can say myself by just kind of taking that number and copying it down and then subtracting and scroll up to that number and copy it down. And so I get 3.91 times 10 to the negative 4 newtons would be the net force on this thing. Oh, I was going to look up that solution you guys told me, broken into 8 parts. I'll have to do that in the next break. But if I scroll down to the solutions, you had made a comment that Don's was a little confusing to you. Number 4. Ah, there it is. He's got the same number. What did he do? What? Oh, I went too high up. That's number, okay. So he did, yeah, he did 1 and 2 exactly the same way. And then, oh, and just quickly said, and that must be a T and a B. Let me make mine a little bigger. Okay, yeah, so it's T and a B, top and bottom cancel. Okay, good. he just kind of crunched it all together. It didn't look like he did much work, but yep, good. Hope that
Awesome.
helps.
Can you show me how you found the direction of the magnetic field one more time?
Sure, sure. And let me, I'll get a new piece of paper here, but let me also remind you and everybody else listening, or who might listen later on, anytime you have a cross product, it's the same right-hand rule, okay? So going back to last semester for you, you first came across the right-hand rule right when the pandemic hit. So I don't recall, I kind of picture Eugene over there, asking questions at that one table there on the side. And then we were just getting to this hard stuff when the pandemic hit. So I don't recall ever doing a cross product with you. But the two cross products you would have seen in 121 involved mechanics. And one was a torque and one was angular momentum. And it's not important to review those. What's important to point out is just the general math idea that if you list two vectors, I'll just call them A and B, and you're looking for C, here's what you do with your right hand. You start here with your right hand kind of in an open position. How can I describe this? In the offering to shake somebody's hand, how's that? You use your right hand, you open up your hand. Of course, it's a pandemic, so we're not allowed to shake hands anymore. But before the pandemic, you would shake hands, you would extend your right hand and be in this open spot. So start that way in an open spot. And then think of your fingers as pointers and try to find where the first one is pointing, okay? And that's where you want to put your fingers. So if I come back to this problem and this drawing, I have a cross product that has an L cross a B. So I would want to start with my hands, like I'm shaking hands with somebody. And I'd think of my fingers and I would have little pointers and they would point in the direction of the current. That's what the L vector is. So if I look at wire number 1, that means I would be pointing it upward, okay? So my fingers would go upward. Now keep in mind, with my fingers pointing upward, I could adjust my wrist in all kinds of ways. I could do this, so my palm is flat on the paper. I could go back to how I originally started, and I'm kind of doing a karate chop on it, and my fingers are still pointing in that direction. I could go this way where my palm is up, but my fingers are still pointing. So there's a lot of ways I can adjust my wrist, but the first step is to say, where do I put my fingers? Right. So I'll say it again. The first step is put your fingers, in this case, pointing up, because that's the direction of the current. Now, the second thing is to rotate your wrist. Let me come back to what I was starting to show here, is that after you put your fingers in the direction of A, you always leave your fingers in the direction of A, but you rotate your wrist so that when you eventually then close your fingers, which of course you close your fingers towards your palm, you will be doing it towards the vector B. So sometimes people like to say rotate your wrist until your palm is in the direction of B. And that's fine, but I like to say, rotate your wrist so you can close towards B. So coming to our problem, so I'll say it again, that first vector is the current going up, so I put my fingers up. And so with my right hand in this position, if I close my fingers are closing kind of in I'll call it a negative x-axis, and that's not the direction of the B field. And so my wrist is not in the right position. My wrist needs to be in the right position so I can close my fingers towards B. And in this picture, B is going in. You might call it the negative Z direction. So this is not right. And for that matter, this is not right. I'm closing my fingers towards a positive Z. What would be right would be this way, my palm down, because I can close my fingers then downward, and that's the direction of B. I'm closing it down. And then once you do that, then your thumb is the direction of C.
I'm actually with you on the cross product. I actually meant to ask you the direction of the magnetic field.
Oh, okay. Sorry.
Sorry about
All right.
that.
Yeah. Okay. So, all right. Well, if anybody else needed that, hopefully that would be helpful. But okay, now, so the other right hand rule, I call it right hand rule number 2, is starting with your right hand in kind of the thumbs up position. Not, not the shake your hand, but the thumbs up position. And when your hand is in this kind of pattern, your thumb is straight and your fingers are loops. And I don't know if you want to call them circles or ovals or squares. It doesn't really matter. But what you do is you start the problem and you say, okay, which is representing, that is my thumb or my fingers, the pattern of current that I have. So things that go in a loop, and so this toroid has the current going around in a loop. So I would say my fingers are the current for this case. If you remember, I think you asked about practice problem number 5, and I had that sheet. In that one, the current were straight. So I was using my thumb to represent the current, okay? So I want to make it clear that it's not always your fingers or always your thumb that is the current. You've got to look at what configuration do you have. So in this problem, which I guess is number 4 on the practice test, the current is making a loop. So I would use my fingers to represent the current. Whereas number 5, we had currents in a straight line. So I would use my thumb to represent the current. But so I don't confuse you, let me not focus too much on number 5. Let me go back to this one. All right, so here's what I would do. I would start off and say, look, the current is going in a loop. So when I hold my right hand, my fingers represent the current. I'll leave the right eye. So there is the current, okay? And if I hold my right hand, my fingers are following the current, my thumb will give me the field. So let's take a look at what I have. The current is going around in a counterclockwise direction. So if I hold my right hand like this, right next to it, I match it perfectly, right? My fingers are going around, oh.
Yeah, I was thrown off because I thought it would be inward. Or, excuse me, out of the page.
Yes, thank you. And let me encourage you. You instead of just asking if you understood it, you should have just been more aggressive and said, hey, Dr. Young, I think you held your hand wrong.
Yeah, well, I didn't want to interrupt you, and I thought I had it wrong, so.
Sorry about that. I wonder what I did. Now I have to go back and look at the video, but I don't know why I got this in my head. But but in my head, I visualized it backwards. My apologies. So everything I just said about this one is the reverse. This field should be out, which means these forces would be out for number 1 and in for number 3 and up for number 2 and down for number 4. Now, fortunately, 2 and 4 would still cancel off. 3 is still going to dominate. So the final answer would still be this one. But it would now be in the inward direction.
Okay, awesome. Would you
Wait,
mind?
hang on,
Oh,
I'm
go
sorry,
ahead.
Judy. I just wanted to look at the solutions here. Oh, and I got careless. I didn't even read what the direction. I just saw the number and said, oh, we match. But he's got it directed towards the center. And yeah, if I had seen that, I would have realized it. But, so you know what's going on. That's good, Gina. And I apologize.
Oh, no problem. I was going to ask you, if I was asked to calculate the force on the top or the bottom, would the integral be from, would the bounds be the distance from the center to the left edge to the distance from the center to the right edge?
Oh, yeah, well, maybe it'd be easier if I'll just, yeah, set it up here. Okay, so I would do this. I would say, okay, if I was asked to get the force on, as you said, number 2, I would say it's the current in number 2 times a little segment of number 2 crossed with the magnetic field. And then if I just did magnitude, that's a vector. And since we have corrected ourselves here and said, okay, it's up. So I'm not gonna worry about direction. But if I just did the magnitude, I'd have the magnitude of DI, then a little dx, and let me just say magnitude. Then it would be the magnitude of the field, and then it would be the sine of the angle between them. And so the current in it would be the 2 amps, but I'll just leave it as currents. I'm going to leave this as the magnitude of dx for just a second, okay? I think you'll see why, but here now is the field from the toroid, and then the sine of 90 degrees. But I think I'm finally getting to your question, because your question said, what would the limits be? And before I put the limits, I just want to point out that this here, this R, is really the distance away, and there's a connection here between the dx and the dr. So what we might want to do then is leave this as an R, but change the dx really to a dr, because I'm going to now then really call my x-axis as measured from the center of the toroid. And so that's kind of one of these things that I talk about. You got to interpret or read the math, because when I just change something to dx to dr, that could lead to confusion. Like, whoa, wait, what are you doing? And I'm not doing anything fancy, because dx is just the distance along this wire. But since the wire is along the direction of the radius, the dx and the dr are the same thing. So for this case, I'm going to just quickly just change a dx to a dr and not really write any kind of formula. There's no substitution in it. It's just, what do we mean by that? Okay, so then I would have the 2 currents, and I guess I should call that current 1 and current 2. So current 1, mu naught, the n, current 2, so I can write the dr here, because I do have one thing that I want to be a little careful with. And by the way, there you see the integral of dr over r. Remember, I think in passing I said that wouldn't be too bad. It would just be a natural log. But you were asking about the limits. Okay. Now, when I look at number 2, it kind of looks like if I go in the direction of the current, I'd go from a big number to a small number. And nothing's really wrong with that. So I'd go from 0.0 0.085 to 0.065. But remember from calculus that going from left to right is the opposite of going right to left. And I want to make sure right here, when I did the cross product, that I have the absolute value. And if I just drop this absolute value sign without much thinking, I'm actually going to get a negative number. And that's where a mistake could easily get made. So maybe I should put the absolute value across the whole thing. And then it doesn't really matter which one I put as my first and my, my beginning and my end. One will give me positive, one will give me negative, but what I want is the absolute value of it. That's what I did when I took the cross product. Because going back to a cross product, the magnitude of C is the magnitude of A times the magnitude of B times the sine of the angle. So once I did this absolute value thing, I have reduced my formula to only getting a positive number and only getting the magnitude. I can't get the direction, which is why I always do the right-hand rule to get the direction. So maybe a little nitpicky here, but you could have just ignored the absolute values and set up your limits either way you want. And no matter what you get, just make sure you take the positive one when you're all said and done, because you are solving for the magnitude of the force. You should definitely only get a positive number. Which I don't know if that was exactly your question. Your question was, what limits do I do? And I guess I'm trying to say it doesn't matter, because we just got to take the absolute value. We just got to go from one end of the other, one end of the wire number 2 to the other end of wire number 2.
All right, that makes sense.
Yeah.
Thanks again.
Sure.
I have a quick question on this problem.
Yeah.
When you are filling out that integral, why don't you have to compensate for the fact that that top component doesn't lie in the same plane as your point? Why don't you have to do any Pythagorean theorem, like with a line of charge, if that point was not on the same?
Yeah, okay, yeah. Now, I get you. Be careful with this R. I think you're asking that because you're kind of misunderstanding what this R means.
Mm-hmm.
Let me draw a picture. So here's kind of the cross section of the toroid. And here is the line of symmetry. R means the distance from this axis.
Okay.
Yeah, and I think so. This wire back here in this original picture that I've gotten so messy now, I'm measuring R from here. I am not measuring, as you said, doing a Pythagorean theorem, measuring up from here.
Okay.
I guess another way of saying this is the R that you would do in cylindrical coordinates. So it's how far are you from the z-axis. It is not the R as spherical coordinates. That is, how far are you from a point, the origin? Yeah.
Okay.
Good. Yeah, actually, that's a really good question. I can really see how you could confuse that R, and it only makes sense if you go back and look at the derivation of this equation and see that they're working in cylindrical coordinates to get that R.
Okay. Cool. Thank you.
And so, yeah, so as a side note on all that, that also would mean this, that if I came out to here and said, what's the magnetic field here? This vertical green line would have, every place on it would have the same strength of the magnetic field.
Okay, I think that's kind of what you were illustrating in your lecture videos when you would go up to that pole in class and say
Oh,
everything's similar, or maybe I'm just confusing a bunch of different things.
no, no, I think you're right. Yeah, yeah, I think so. That's kind of that idea is, yeah, that right. And you bring up things that always keep coming back to me when I work with students is, it's, since I derived it, I've done it so many times. I indirectly, know that I'm talking about an R in a cylindrical coordinates, not R in a spherical coordinate. But for the beginning student, that's tough.
Yeah, okay.
Yeah.
Thank you.
Mhm. All right, so let's see. Um, so next here looks like Max, we have, how about we do question on practice exam number 2 and number 3? Okay, yeah, sure. Right.
It's just like test 2, so just the first practice exam, I guess you sent us, number 3.
Oh,
Like
say that
it's the
again.
same.
So it's practice test number 2, problem 3. Is that?
Yes, yeah.
I was reading it wrong. Yeah, thank you. Okay, so
Is there
practice.
a question above that one who might have asked first?
What? Go ahead. What? Yeah. Gina?
I think Anthony might have a question before that one.
Oh, did I mess up here, Anthony?
Oh, yeah. Hi, I'm back. Okay.
Was I working with your question and I missed something?
I think you were working with the toroid, and then I asked this one about number 65.
Oh, yeah. Okay. Yep. Sorry. Yep. I skipped it. Now I see what you're saying. Thank you, Gina. Because I was when I jumped back, I for some reason mentally skipped over that one. All right. So I'm going to do chapter 30, number 65, and then we'll go to that practice test number 2. So let's come over here to chapter 30, number 65. Yes. And talk to me as I do this. I want to do it maybe a little fast for time-wise, because something like this, number 1, is too long for the exam. But number 2, this is one that I want you to study. I want you to see. I hope I communicated to you guys that this is the start of trying to understand magnetism of materials. And so it is kind of getting your feet exposed, or your feet wet, if you will, and get you guys exposed to what you will do at the next level. Because all the magnetism we are doing is magnetism of free space, which is hard enough in itself. But there's a series of problems that have to do with this section on the magnetism of matter. And like I said, I think it's really important that you see it, but not be tested on it at this level. You'll be tested on it again. All right. So let me give this one a shot here. And this says in 65 that we have a sphere, number 65, I'm gonna write this down, time 112, okay, that is rotating. And by the way, a little history here, when scientists began to realize that the electrons were responsible for magnetism, it kind of threw them for a quick loop at first. They're like, whoa, wait, where's the charge? How is it moving? And then they realized that, just if an electron was a ball, and now we don't really think of it as a ball anymore, but if it was a ball, this is their model. They said, what if you had a ball and it was spinning? How much of a magnetic field would it make? And so this is saying that a sphere of radius r has a uniform volume charge density rho. Determine the magnetic field at the center of the sphere when it is rotating as a rigid object with an angular speed of omega about its center. Okay. So I'm going to do this little trick, if you will. I'm going to say, we're trying to find the magnetic field at its center. So let's call that our point P. And let's do this. Let's just go up a little distance and look at the charge that makes a ring. So as that charge moves around in a ring, it's going to make a magnetic field. Then I'm going to say, well, wait a minute, a bunch of rings added together would make a disk. And then a stack of disks would make the sphere. And so it's going to follow this way. I'm going to go, what's the magnetic field from a ring? Then I'm going to say, add up a bunch of rings, and you're going to get the magnetic field from a disk. And then I'm going to say, add up a bunch of disks, and I'm going to get a sphere. Okay, so that's the game plan. So let's start with the easy one here, the ring. And the equation that was derived with BFs of art looked something like this. So let's take that as our starting point. And if you go back to this derivation for the ring, A was the radius of the ring, I was the current in the ring, X is the distance along the axis of symmetry. So I'm going to come back and redraw my sphere. I'm going to put the point P at the center. And I'm going to make a ring up here somewhere. Maybe I'll call this the x-axis, the y-axis, and coming out the z-axis. Okay. And for starters, I will just say that this ring has a radius, and I don't like to usually work with A's, so if it'll be okay, I'm going to say it has a radius of lowercase r for a moment. And so this equation, which is the magnetic field for a ring, I'm going to write this way. I'm going to write it as a mu naught. And I'm going to be kind of careful here, and I'm going to say current in the ring. And I'm going to write this then as r squared. And the way I made my grid, the x in this equation, the distance from the plane of the ring to the point in question, would actually be along my y-axis. So if you'll let me change my x to a y, I'm going to write that as a y squared. So really haven't done too much here in this step other than to change the a to an r. It makes me feel a little more comfortable. The x to the way I labeled it out, a y, and also to focus some attention on what do I mean by the current in this ring. And that's where I'll have to look here, because this then might be thought of as this way. The current in the ring is defined by the charge that would be in the ring divided by the period of one revolution. So remember, this thing is rotating at a speed of omega. So if you look here at this ring, the whole reason this ring has charge is because this is a charged ball, and there is then a charge density. And the charge density then would be the charge in the ring divided by the volume of the ring. So I'm going to say, all right, here's the current in the ring. Let's do this. let's replace this with the charge density times the volume of the ring divided by the period. Now let's talk about the volume of a ring. If you took, lack of better option here, let me take the charging cord to my laptop and you know, make a ring out of it. Here's kind of my ring. The volume of this ring is its length, and then of course what you might say the cross-sectional area of this. So in my case, I might call this ring having a up and downward thickness of dy and a back and forth along the x-axis here, a dr. I'll call it a dr because I've been using r for the radius of the ring. So I would say the volume of this ring then is 2 pi r, that's the circumference. Then the thickness in this direction, and then the thickness in this direction, which is a dy. And in a moment here, I'm going to just focus on adding up the drs. A bunch of rings, adding a bunch of rings gives me a disk, so I won't even add in the y direction yet. But then I will add in the y direction. All right, so I'll just leave that alone. But here I'll also do period. Now, here I need to go back to Physics 121. Angular speed is the one rotation. So one rotation is a radians of 2 pi and the period. So we could write period then as 2 pi over omega. So down here, I'm going to put 2 pi over omega. So that is the current in the ring, and that's what I'm going to put into this equation. Okay. So the magnetic field from a ring, you might even say a small magnetic field from the ring, because I'm going to add up a bunch of rings to get a disk here in a second, is equal to, and so I have this mu naught, and let me just put the r squared first, and I'll put the current from the ring in just a second. This is a 2, this is then the y squared, this is then the r squared to the 3/2 power, okay. And then I'm going to put in this crazy stuff. And I'll simplify it a little bit by canceling off a 2 pi. And the omega will go on top. So this is omega, this is the charge density, this is the r, this is a dr, and this is a dy. Okay. And so now I can say that the magnetic field from a disk is what I would get when I added up the magnetic field from a bunch of rings. And then this is my ring. I've got the mu naught. Why don't I put the r's together? So that'd be r cubed. There's the omega. There's the rho. There's the dr. There's the dy, which isn't going to come into play until I add up the disks. That's the thickness of the disks to get the sphere. And then this is a 2, and this is a y squared plus a r squared to the 3/2 power. Okay. And I'm going to add it up. My limits are going to be from 0. So the first little ring up here would be a radius of 0. And I'm going to keep going until I get to the edge here. And I don't want to call that capital R because that would only be capital R if I was adding up it right at the equator. They use capital R for the radius of the whole sphere. So why don't I just say from 0 to little r? I hope that doesn't confuse it. I could put a prime here so that these are primes and they come out to be different, but they're kind of meaning the same thing. So maybe I won't put a prime like I did on the other problem here. But as I then go to step number 2 here, I've got a tough integral here. So I've got a mu naught, an omega, a rho. Those are all constants. I've got a 2. But stuck inside of this integral is an r cubed, a dr. I'm going to put the dy over here. Again, that's something we, and if we just had a disk, I would have never set it as a dy. I would have just said thickness of the disk. But I know that I later on got to come up and add the thickness of the disks together. So let me just leave that y alone there. So I got an r cubed over a dr, and then this is the y squared, and then the r squared to the 3/2 power. And so I'll say it again, things like this are screaming trig sub, but don't actually do the trig sub. Go and look it up. So we were looking this up earlier. Let me go back to the textbook. This one may not actually be listed here. No. Well, that's a bummer. It makes me kind of think I did it wrong. There's the solutions to this. Let's see, it's on the same page as the test review. Let me turn off the test review and go to number 65. Oh. Did he do a U sub here? Of course, he did a V. Yeah, let me try it. It didn't look like a U sub to me, but I'm going to try a U. What if I let U equaling y squared plus r squared? Then du equals to 2r dr. So that this integral downstairs would be u to the 3/2 power. Oh, it's pretty okay. Okay, wait a minute. Then we could write this r cubed dr as, of course, r squared times r dr. And so this right here, the r dr would be du over 2. And the r squared would be u minus y squared right there. R squared would be u minus y squared. Okay, so this becomes a u minus y squared over du over 2. Ah, so it is a u sub. Wow, didn't see that coming. Okay, so this first term, let me just write it as u, and then this is a 1 minus 1.5. So I'll write it as negative 1/2. And then this would be the y squared, and then this would be u to the negative 3/2. And then I would have the du, and then let me not forget this other 2 over here. So I'll put that a 4. And then so I get mu naught omega rho dy over 4. And then when I do an integral, let's see, you add 1 to the exponent and divide by the new exponent. So you add 1 to the exponent and divide by the new exponent. Okay. Then I get the mu naught, the omega, the rho, the dy over a 4. Let me write this then as a 2 upstairs. And this is u to the 1/2 power. So this would be y squared plus r squared square root. Okay, so that would be when I put the u to the 1/2 power back in. This minus and this minus make a plus. This 2 flips up to the top, so that's a 2. That's a y squared. And then this would be downstairs. And so it would be the square root of y squared plus r squared. And then, of course, my limits were, what were they? 0 to the radius r. Okay. And then maybe I'll take the factor of 2 out and cancel again. And so this first term would be the square root of y squared plus r squared minus the square root of, if I put in a 0 here, I just get, well, the square root of y squared, which is just y. And if I put it in here, it would be plus, this would be y squared over the square root of squared plus r squared minus, and if I put in a 0, I get a y down here and a y squared, that makes a y. So minus a y. Bummer, I was hoping those would cancel off. Okay, well, more calculus to do here. Okay. And then mu naught omega rho dy over 2. And it looks like, should I try to get a common denominator here? Maybe I should. These y squared plus r squared to the square root might be a common denominator between those two. I'll just put a 2, negative 2y for those. But this is already over that common denominator. And so this I had to multiply by the same thing. So this would be just a y squared plus an r squared. Mu naught omega rho dy over 2. And it looks like then I'm going to have a 2y squared plus an r squared. Ooh, maybe I don't want to get a common denominator. Maybe I should leave that alone. Okay, so forget a common denominator, because I got another integral to do. Okay. All right. So I would say at this point, I've got a lot of pages here. I have the magnetic field from a disk. And so that's it for the disk. I won't rewrite it, but what I'm trying to get at is then to get the magnetic field for the sphere, I've got to add up my magnetic field from my disk. Okay, so I'm hoping those square roots are thinking of Pythagorean's theorem, but watch this for a moment. Keep this equation in mind. The square root of y squared plus r squared. And let's come back. Where the heck is page 1? I didn't write page 1 here. But if you come all the way back to this original picture, remember what I just did is I just integrated out to this edge. So this is the r. And remember, this going up is y. And this then would be the hypotenuse, which is the radius of the sphere. So in other words, y squared plus r squared would be the hypotenuse squared. So this right here is actually r. And then I'll put minus 2y here. And then this would be y squared over r. Yeah, I like that. Now that looks something a little more manageable, if you will. Okay. So what's of course nice about writing it in terms of capital R is when I finish this problem by saying I'm going to add up a bunch of disks, okay, I'm going to be, starting down here and going up and up and up and up. So I'm going to add y going from 0 to capital R. But of course, as y goes from 0 to capital R, y is changing and r is changing. But what doesn't change, so what was looking like was going to be hard, was as this y and the r were changing, they changed in such a way that they remained a constant. So write it as things that are a constant, which is this r. And so I'm going to go from 0 to capital R as I add up my disks. Now, to be quite honest, that's only half of it, because adding up my disks from here up to the top is the top half hemisphere. The bottom would be identical. So if I'm going to go to 0 to R, maybe I should double it to get the total. Yay. Okay, so this looks like it's going to be a little easier integral to do. The 2's cancel off, and I get a mu naught, the angular speed, the charge density. There's the dy, and so this first term would just be r, and when you integrate it, you get y evaluated from 0 to r. This one here would be minus 2, and then we'd get a y squared over 2 evaluated from 0 to r. And then this one, oops, I'm off the screen, sorry. And so this one would be y cubed over 3, and then the R was already downstairs, evaluated from 0 to R. And I get a mu naught, an omega, a rho, and then this term would be R, this would be an R, which on that R would be R squared. This would be minus, I put in an R, so that'd be minus an R squared and a 0, so minus R squared. Okay, that's going to cancel off. And then this is going to be R cubed, which becomes an R squared over a 3 minus a 0. That cancels off. And I get a mu naught, an omega, a rho, an R squared over 3. I'm tired. I hope I didn't lose too many of you. Hopefully there's something decent there. And I should check the answer. This had a lot of math in it. Let's see, mu naught, rho, omega, R squared over 3. Yay! Okay. So I hope I didn't bore or lose too many of you guys in the math. Anthony, that help at all?
Yeah, it proved to me on how this is not going to be on the test.
All right, well, that's true. That wasn't the point here. But some good history, this is exactly what the early scientists thought of the electron, that it was a little ball, it was spinning. Like I said at first, before they even realized there was a magnetic field, then they discovered it had a magnetic field. They were like, what? And then they realized, hey, this could be, like a basketball spinning on somebody's finger, hey, that's a moving charge. And then they went through this map that we just went through and got the magnetic field. And they actually did the reverse. They actually then measured the magnetic field of the electron so that they could go in reverse and figure out what the radius of the electron would have to be. And they were trying to figure out what the size of these little tiny things are. Now, it turns out that it's much more complicated, and we can't think of them as little tiny balls. But that was their thought process. But yeah, and you're right. It would be too long for a test. But also, let me point out, I hope you always caught that bigger picture of why you're learning your calculus. Did you notice that what I did is I started with what I knew, which was the magnetic field from a ring, and then I built on that. A ring, then add a bunch of rings, you get a disk. Add a bunch of disks, you get a sphere. And once you really get the gist of calculus and the power of it, you begin to realize that there is no shape of current that you can't calculate the magnetic field, because you just add up a bunch of little things. We did the same thing with Coulomb's law for electric fields. I mean, if we know the electric field from a point from Coulomb's law, anything else, you give me any shape. I mean, you can give me like the letter M and charge it up, and it's got all these shapes and these slopes, or whatever the shape is. The letter S, you just have to add up all those pieces. So it may be hard and maybe a lot of work, but theoretically, it's doable. All right, but again, I hope I made that clear in that video that this one not only would not be on the test, but it has to do with the material of matter. And so we're crossing that bridge from this semester to next semester. And so I want you to see them, work on them, but not necessarily before the test. That's really kind of the thing you should look on as you get started for the next chapter. All right, well, let me jump over to Max here. Max, let's, what was yours? Practice test 2, number 3. Let me write down the time here. I'll get started with yours at 1:43. And I'll put page 1 and practice test number 2, problem number 3. Okay, so jumping back here, and I think I left the practice test because I looked up the solution. Let me click back here. Practice test number 2, and then scrolling down to the second test.
Or just
Okay.
the, I guess it would be the first test on that PDF.
Oh.
It's called test 2, and then the other one's called exam. I just went by that notation. But
Oh, okay, okay. Yeah, I hear what you're saying.
sorry for the confusion. So it's
Yeah, yeah,
it's
yeah.
that
No,
number
no
3
problem.
long
Okay,
straight
so,
wire with the radius bar.
oh, yeah, yeah, yeah. Okay. Now I'm gonna make a wild guess here because somebody else was asking it about it earlier, and I spent too much time doing the left-hand side of the equation. So I'm going to focus on the right-hand side of the equation. But let me begin by saying when the problem starts, it says a very long wire, okay? And to me, that sounds like the Ampere's law type of calculations where we have this symmetry argument.
Mm-hmm.
Too much on my phone, there we go. And we have these symmetry arguments. And so I'm going to do the same thing. And so on my little piece of paper here, I'm going to draw a cross section. I'm going to try to make it three-dimensional going backwards. I'm going to just say the current total is I. They don't really give me any of that. They just say the total radius is R, but they want to know the magnetic field inside. So I'm going to draw an Amperean loop in blue. It's nice circular loop. And I'm going to then try to solve
Do they want the
Ampere's
magnetic?
law for
Do
this.
they want the magnetic field, or do they want that? They're asking for that value of n that they gave in that variable
Oh,
current density.
okay, fair enough. They want to know, right, the value of n, sorry, when the magnetic, that would make the magnetic field constant inside the wire.
Oh, okay, gotcha.
Yeah, so sorry, I didn't say that well. But what it does tell me is I want to then solve this equation, not for the magnetic field, but to remember that the magnetic field is going to be constant. And they want to know then how the current is distributed, basically. That's what they mean by that power of n. How is the current distributed in here in order to get this to be a constant? So that's why I was saying I should probably focus most of our discussion here on the right-hand side here, not on this left-hand side. So I'll start with just kind of taking the dot product, but unless you have a question, I will do the same thing, an argument that was done for the wire when the current was uniformly distributed. And that is, if you imagine yourself anywhere on this wire, the current would look the same to you no matter where you are on this blue Amperean loop. And that step would justify you saying that the field is a constant on that loop and you can pull it out. Now in this problem, I could even go one step further. I'm trying to get a current distribution that is such a pattern that the magnetic field would be a constant everywhere inside, not just on the blue loop, but even inside the blue loop and outside the blue loop, but not outside the wire. So I'm going to use that as a chance to justify why I'm going to pull that out. And then on the left-hand side, just quickly write 2 pi r, where r then is the radius of the Amperean loop. And so nothing different on this side that you hadn't already seen for a uniform current distribution. And what they're trying to say is in a superconductor, the distribution is not uniform. It is nature does it. Nature does it in such a way that it wants to get the field to be uniform. And it, as you're going to see, it's going to take a non-uniform current distribution to get that. So here, I think, is really the main part of your question. So to get the amount of current that is inside of this Amperean loop, let me draw a cross-section of the Amperean loop. So here might be the Amperean loop. And if the current is not uniformly distributed, I might think of the total currents as the sum of a bunch of rings. So I am going to say, let's figure out what the current is in one of these rings and add up all the rings. And when I say add up all the rings, I mean add up all the rings to the Ampian loop, not all the rings to get the whole wire, but a ring and 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 a ring. When I add up all the currents in those rings, I will then get the current inside of the Ampian loop. Now, why did I pick rings? Well, I picked rings because they said in the problem that the current is distributed according to this equation. And what that means then is if you go radially outward, let's say you go to the left or the right or up or down, it doesn't matter which of those four directions you go. If you're the same distance away, you get the same current density. So I think the current density along those rings is the same. Maybe a drawing might look a little bit like this, if you will. If I did a bigger ring that I have some space in between so I can kind of see the thickness of the ring and kind of color it in. I'm claiming then that current density is defined as currents over the area. So I can think of the current in a ring as the current density of that ring, then times a little bit of area of that ring. And so easier than the last problem, but like the last problem then, I can look at this ring, and let me just put the equation for the current density. But the area of one of these rings, if you kind of imagine cutting this ring and straightening it out, the area of it would be its length, which I will represent as 2 pi r, and its thickness, which I'll represent as dr. So I can write the area as 2 pi r dr. And now, to do the calculus, I might pull out the constants and do my integral. And when I integrate this, you add 1 to the exponent and divide by the new exponent. Now remember, on this side of the equation, the right-hand side of the equation, there is still this over here. There's the b and the 2 pi r. So if I cancel off the 2 pi's and one of the r's, I get the equation for the magnetic field listed in terms of n. And as you pointed out, the point of this problem is to find n. And here is the final last step, is we are told that nature distributes the current so that B is a constant. What does that mean? Well, maybe a good math review might be important. If I have y versus x, if I plotted y equals to mx plus 1, that's a line, right? If I plotted y equals to x squared, that's a parabola. Y being a constant is a straight line. When do you get a straight line? Well, you get a straight line when it doesn't depend on the x. Or put another way, when you get x to the 0 power. You see, if I had n equaling -1 here, this would give me b equals, and it would be a mu naught, and then a lowercase b, and then over an n plus 2, and this would be r to the 0. R to the 0 is just 1. There is no r in the equation, and that's the final step, the mathematical key step. That's how I know what n has to be. So n has to be a -1. So the current distribution would have to be something that would look like this, b over r. And this is actually a very realistic problem that happens in superconductors. That's kind of why I thought it was a good problem. This is nature in superconductors do not make the current evenly distributed like they do in regular conductors. They make the magnetic field evenly distributed, and therefore the current has to have some kind of function to it, and this is the function that occurs in the superconductors.
Yeah, that makes a lot of sense. Thank you.
Yeah. So whatever. Yeah.
Sorry, I interrupted you.
Sure. What?
Could you just explain why you did JDA about halfway through the page?
Oh, yeah. Okay, so you're talking about right.
It's
Here,
like the
green.
yeah, right there.
Okay, and it's tied to this right here. Okay, and I'll flip back and forth on a new page, but you got J we first saw but haven't used it too much. So I guess I'm kind of asking, do you remember what J is? J is the current density. So J is saying if you take the currents divided by the area, and so over here, area, you have the definition of J, okay? And it's a current density.
Okay.
And so I'm trying to find the current, and so I guess I would replace it with this. I'd say if I take the current density of the ring, that would equal to the currents in the ring divided by the area of the ring. And so if I bring this over to here, I would have current density of a ring times the area of a ring is equal to the currents of the ring. And so that's the step. Now, the only thing that I have different on page 1 that I'm doing here is these rings are, I'm thinking of in terms of calculus, so they're really, really thin. So we might call it a dA. But when we make a ring and we go to calculate the area that a ring occupies, and I'll just color it in, it's best to see that by maybe imagine cutting the ring and straightening it out. And so its length is its circumference. There's the 2 pi r. And then its thickness is a small length along the radial direction. So we call that a dr. So this would be the J, and then this would be the 2 pi r dr. So that equals the current from a ring. And so that's what I did back here on on page 1, so I'm going to add up the current on a ring, and then down here, I got the J, and then the 2 pi R dr.
Okay. So if that was like current on a sphere, you could use J times volume of the sphere.
It's
Or
still
like
the
just
area. So if the current was flowing like in 3 dimensions out, it would go through the surface area of a shell. So it'd be 4 pi R squared, not the volume.
okay. Oh, okay. That makes sense. Cool. Thank you.
So it's always the surface that the current is flowing through. And then you got to look at your geometry, yeah. All right. This is a long problem. Yeah. Yes. I saw you shoot that up there when I was doing that long integral for 65. Yeah, totally. I was keeping my fingers crossed the whole time going, oh, I hope I don't make a little mistake here. This could look bad at the end. So, and yeah. And I'm glad they made it easy. I did not see that one was going to be a trig, just a simple use of, but it did. That was great. I went to look it up and it wasn't there. And I thought I was going to have to Google it. And I guess that would have worked too. But it was more surprising that it was a use of.
What is the page you reference again to find those integrals?
I always use Appendix B. Let me look up the page number. If you got the PDF, I know you have the PDF version since I sent it to you. And it on the PDF, if you go to page, well, on the hardcover copy, it would be page A18. I guess A for Appendix 18. So it's way at the end of the book. And on the PDF, it would be page 1447.
Okay, thank you.
And also a bigger picture. Keep in mind that that whole appendix, well, Appendix B, is all math review. So you've got your trig identities, you've got your trig double formulas, half formulas. You got some geometry stuff in there, like the surface area of the sphere, and it's 4 pi R squared. They even have simple ones like the properties of logarithms, in case you've forgotten some of the properties of logarithms. And so it's good for the students. Those aren't usually the ones I use, but I do use this table of integrals. It's not a very complete one. It's only 1 page. It's got 2 columns, but it's got most of the common ones. And I think your author made an effort to list all the ones that are used in the textbook. So if I ever come across a problem in the textbook and it's not in this table, I pause for a moment and say, uh-oh, am I doing something wrong? But he also says here he doesn't bother to do any of the U subs in here. So that should have been my clue that the one I was doing could be done by a U sub because it wasn't listed here. It's just the one I had looked so hard, it didn't look like a U sub. But it was. All right, so let's see. Come back over here to the Zoom. Nice. No more questions at the moment. That's fine.
I have.
Hey. Oh, I guess it's break time, huh? Were you going to ask a question?
Yeah, I had a couple just quick conceptual
Sure.
questions that I was just curious about.
Yeah.
Whenever they're talking about like shooting a positively charged particle, I was a little curious. How do you create a positively charged particle? Is it a proton or is it an atom that has been stripped of electrons?
Oh, both of those would work. It could also be some of these exotic materials that we don't find normally in our everyday world, called a positron. But why don't I just start with the easiest one? A proton is really easy to make. you start with hydrogen, and hydrogen has a single proton as its nucleus and an electron.
Mhm.
And if you end up shooting other electrons at it, they tend to hit each other and knock each other free, and then you have this free proton.
Oh, okay. But so in terms of current though, it's always just electrons. It's always
It's better if you say it's always electrons if you're in a solid. See, because if I can kind of draw a picture here, an atom always has a nucleus, okay? And by the way, the extension on the free proton is, that's what you said. Could it just be an ion? Yeah, if I had something bigger that had, say, well, let me go with lithium, that has 3 protons in the nucleus. I guess it also has 4 neutrons, so I'll draw those and color them in, but they're neutral, so they're not really part of this discussion. But there's my lithium, and the lithium then would have 3 electrons around it normally. And if you just shot the lithium with a bunch of electrons, they tend to rip it away. And if they rip one away, you would still say you have a positively charged object. We would write it as a lithium plus. If you hit 2 electrons off, then you would have lithium plus 2. And if you were successful in removing all 3 of them, you would have lithium plus 3. But you would essentially collect it the same way as you did here for the protons. You would have a plate over here that is negatively charged. So once you strip off the electrons, that pushes the electrons even further away and pulls the proton this way. And then usually you put a small slit in here, and most of them just collide right back on the plate and don't do anything. But some of them just happen to be at the right angle. They go through a little opening and go shooting off. And it doesn't have to be, I mean, if it's the nucleus of hydrogen, well, then it's a proton. But if it's the nucleus of lithium, and it doesn't even have to be the whole nucleus, if it was just the nucleus, we'd call it lithium 3. But it could be 1 electron is hanging around, because it's really hard to get the last electron. It's actually even hard to get the second one off. So it's easy to make lithium plus. It's very hard to make lithium plus 2 and really hard to make lithium plus 3. But that last one is just really attracted to those. But it can be done. And again, the same thing, if you made a plate that was negatively charged, once you made this an ion, it would start racing towards it. And so that's the challenge of making lithium plus 3, is when you first hit it the first time, you only make lithium plus, and it starts moving on you. And you have to make sure you hit it in time to get rid of the second and the third before it goes through there, before you're going to get lithium 3. Anyways, that's how you make a positively charged object. Now, kind of a different way to do it is really what we were doing. If you remember the very first week, I just took acetate and I just rubbed it and actually teared some electrons off. So if I had a round ball of acetate and I just rubbed it, I would actually have a charged object. But its charge compared to its mass wouldn't be something that would be real controllable or movable. So that's probably an example I shouldn't even have brought up, because I could shoot it in a magnetic field, but it's so massive compared to its charge. It's not like these protons or electrons moving around.
Okay, thank you. I think what I was focusing on is when we were first getting introduced to this stuff, I think you were emphasizing that it's only the electrons that move to.
Oh,
and I think that's more so.
Yeah, I'm sorry. Yeah. Oh, that's what I was saying. I knew there was something else in my mind you had said. I go, what else was he saying? Yeah. So keeping that in mind, if you take a look at a solid, versus a liquid versus a gas, okay? So a solid, the atoms, the nucleus hooked together with another nucleus, and they're all hooked together. And since the positive charges are in the nucleus, in a solid, you cannot have positives that move. Now, the electron can move and go from one atom to another to another. But in a solid, you cannot have positives moving. So most of the time, we make our electronics out of wires. Our wires are solids, like mostly copper, but sometimes we do aluminum and gold and silicon. But so most of the time in our electronics, we have to make it very clear that the things that are moving are the electrons, not the protons. But in a liquid, for example, let's say we're looking at a car battery. And so here's the positive terminal and here's the negative terminal, which the wires are going to come out, and the wires are usually made out of copper. So in the copper wires, I would say only the electrons are moving. But inside the battery, where the sulfuric acid is, there is sulfate ions, and there is also lead ions. And so the lead moves because it can. It's in a liquid. It's floating around, and it's positive. And the sulfate moves. And again, it moves. Not that it's an electron, but it can move. And so our moving charges are actually both positives and negatives. Now, they're not even electrons. They are ions, positives and negatives. So in a liquid, I would say both positives and negatives are moving, and neither of them are electrons. And for that matter, I guess, well, I was going to say none of them are protons, but that's not true because there is some acid moving too, which is just a proton. So, but the positives are moving and the negatives, so you have both. And the gas is the same thing. If you were trying to put electricity through a gas, how about xenon? Like a xenon light bulbs are cool. You have the xenon gas in here, and you make one side very negative and the other side very positive. So much so that the electrons on the xenon actually get pulled off, which of course then leaves the xenon positively charged, and it moves that direction. So again, in a gas like a liquid, both positives and negatives are moving. And usually in a gas, the negatives are the electrons moving. And then the positives are the ion that's left over, the positive ion that's left over after the negative came on. So just to, I don't know if that made things better or easier, but yes, working with solids, only electrons move. They're negative and only they move, not the positive. But liquids and gases, both positives and negatives move. And oftentimes in a liquid, the negative is not even an electron.
Okay. Yeah, I think that makes it pretty clear to me.
Yeah.
Thank you.
All right. Well, let's take a little break, and if I see you guys back at 3, great.
Cool.
Bye now.
Thank you.
Yeah, you're welcome.